Okay, so as in the last video, we did electronic configuration of, the 10 elements, which includes scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. Alright, the electronic configuration which we got of scandium was 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1. Then we got the electronic configuration of titanium. That was 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d2. Alright, then vanadium. The electronic configuration of vanadium was 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d3. Then chromium 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5. Here we got an exception, since if we would have written here 4s2, then here would only 4 electrons left. Alright, then here would only be 4 electrons left, and we know that half filled wait we actually know that half filled orbital is more stable as compared to the full filled. Alright, that's why we removed one electron from here and we gave here. Alright, so electronic configuration of chromium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, and 3d5. Then the electronic configuration which we got of manganese was 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d5. Then the electronic configuration of iron is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. Then cobalt 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d7. Then nickel 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d8. Then copper 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d10. Here we learned about another exception. We filled full the orbital d instead of s, because we know that d would be more stable as compared to the s. Alright, then the last but not the least, the electronic configuration of zinc was 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. Today we are going to read the 4 rules. Basically we have 3 rules. Alright, n plus l rule and Affa principle is same, or Affa rule is same. However, I am gonna separate these all today. So we're gonna read or learn about these rules to fill the electrons to their orbitals or orbits. Alright, so this is basically, electronic configuration is nothing but it is just an arrangement of the electrons, right? It represents the location of the electrons, where are they present actually. Alright, so Appa principle is nothing but, let me write that first. So initially we have actually learned about, we know that in first shell we have only one subshell, so 1s, and s holds 2 electrons. Then in second shell we have 2 subshells, right? 2s and 2p, and s holds 2 electron, p holds 6 electrons. Then in third shell we have 3s, 3p, and 3 d. So s holds 2 electron, p holds 6 electrons, d holds 7 not 7, however 10 electrons. Wait, d holds 10 electrons, and wait, now in fourth shell we have 4 subshells, right? So 4s2, 4p6, 4d10, 4f14, right? So what we made then? We made arrows from down from up to the down, right? It was like this, right? So what we get here, initially the electron will be going in 1s2, then 2s2, then 2p6, then 3s2, then 3p6, then 4s2, then 3d10, then 4p6. Alright, we actually discussed that. Now what does n plus l rule says, right? So n plus l rule says whatever will have the lower energy in it, that subshell will be filled with electrons first, right? This Affa principle tells us that as well, right? That whatever will be the a lower energy width, they'll gonna be filled first. So 1s2 has the lower energy as compared to 2s2. That's why 1s2 will be filled with the electron first, then 2s2 will be filled, then 2p6, then 3s2, then 3p6, then 4s2, then 3d10, then 4p6. Alright, like this the electrons would be filled. Alright, now n plus l rule says that we need to sum the principal quantum number with the azimuthal quantum number and we know that n represents what? It basically represents the shells. Alright, so n means shells, L we have already discussed, those represent subshells, right? Which means we need to add shells to the subshells. Whatever will be the lower energy width, they'll gonna have a less number. Alright, so if I'm writing here 1s, I should not actually write here, it would gonna create a very big misunderstanding. So we know that in first shell we have only 1s, in second 2s 2p, in third shell 3s 3p and 3d, in fourth we have 4s 4p 4d and 4f. Alright, so now we need to add them. Alright, we need to add them. We know that in the azimuthal quantum number the value of s is 0. Alright, so 1 plus 0 gives us 1. Right, now let's count initially all. So 2 plus s is 0, so 2. Alright, 2 plus the value of p in azimuthal quantum number would be 1. Alright, so 2 plus 1 is 3. Then 3 plus 0 is 3. Then 3 plus 1 is 4. 3 plus 2 is 5. 4 plus 0 is 4. 4 plus 1 is 4. Not 4, however, 5. 4 plus, 2 is 6. Then 4 plus 3 is 7. Now see what is, where is the less number initially. So 1 is less number. Let's go with this 1s first, which means initially electron will be going in 1s, right? So 1s2. Now let's see, now what do we have to take? 2, alright, because then the all numbers are greater. So 2 and 2 is of 2s. So let's write here 2s2. Alright, then we have 3 2 times. Alright, if there are same numbers, we need to check their shell number, right? 3 3 both are same in 2p and 3s, but we know that 2 is smaller than 3, so we're gonna consider this first. So 2p6. Alright, then we'll be writing that this 3s, right? So 3s2. Then after 3 we have fourth one, but 4 is again we have 2 times. So initially we need to take this 3p1 because the 4 shell number is larger. So 3p, wait, 3s, 3p6, right? 3p6. Then we have to take this 4s2. Alright, then see the 5 one. 5 1 time, 5 2 time. But this is 3 wala, this is 4 wala. So we need to take this smaller one first. So 3d 10. Then 4s2. Is this 4s2? This is 4p. Alright. So then we have 4p6. After 4p6, we have 6, and that is 4d. 4d, 10, and then, 4f14. Now let's see if this matches this. Alright, initially electron will be going in 1s2. Yes, so 1s2. Then 2s2. Yes, 2s2. Then 2p6. Yes, 2p6. Then 3s2. Yes, 3s2. Then 3p6. Yes, again 3p6. Then 4s2. Again write 4s2. Then 3d10. Again write 3d10. Then 4p6. Again 4p6. Then 4d10. Alright, which is here. Then 4f14. Right, this is how the electrons will be going, which means this is right. So Afbab principle and N plus L rule, these both are same. They basically tell us that whatever shell has the lower energy, those orbitals will be filled first. Right, now the third rule is Hertz rule. He does not say any big thing. However, he just says that if there, let's consider this p1 first. This is, p subshell. We know that in p subshells there are 3 orbitals, right? So 1 2 3, and in 3, wait, let me write that as well. So p subshell, there are 3 orbitals, right? In 3 orbitals there are 6 electrons. Right? So the Hertz rule says if you have how many electrons does not matter. Initially you need to give them one electron. One electron with the same spinning. So this is basically known as one rule. 1 rule. Since we allocate a 1 electron to each orbital, right? Then we need to give another electron with the anti-spinning, right? So this is what Hertz rule says. Then we have Pauli exclusion principle, which we have already discussed in very detail initially. He does not say anything, but he just says that no 2 electrons will possess same set of 4 quantum numbers. Alright, and this we have discussed initially in very detail. Alright, so I don't think we should go in detail now of this. So today we have discussed about electronic configuration, and here finally this chapter completes with all subtopics. You know what, every topic is included in this, and you can find my playlist. It would be there, alright, with I guess 40 plus videos. Now we will be solving MCQs from OETP. I'm gonna get some other resources as well to solve the MCQs. Alright, so this was all for today.